Welcome back. Here we are trying to understand how do we use integral calculus to compute volumes of solids. As in the case of determination of area of some planar regions where rectangles played the roles of building blocks, here in this case the cylinders are going to play the role of building blocks. So how do we now proceed? Like exactly in the case of determination of area, we are going to have three axioms which are going to guide us in understanding these problems. So before going to the three axioms, let me tell you what is a cylinder. So cylinder must have a base, and it is determined by drawing lines that are perpendicular to the base region. And this is how we get a cylinder. So a cylinder has a base, and suppose that the base has area a, and we will always denote by h the height of the cylinder, so which are the length of the lines that we have drawn on our base. So a more particular case that we are familiar with is the case of right circular cylinder. And what is special about right circular cylinder? In the most general case, the base can be any region of your choice. But in the case of right circular cylinder, the base is going to be a circular region, a disc to be precise. So suppose that we have the circular region with radius r, and the height of the cylinder is h. We were always told in our school, without giving any proof, that the volume of this cylinder, this right circular cylinder, is given by pi r square h. More generally, what we are going to assume as our first axiom is the following. So given a cylinder with area of the base a and height h, the volume of the cylinder is given by ah. The second axiom and third axiom, these two axioms are quite similar to that we had in our case of area of planar regions. So what was our second axiom? It said that bigger the region, bigger the area, and here bigger the solid, bigger the volume. So if R is contained in S, then VR, volume of R is less than or equal to volume of the solid S. And if here R can be decomposed into, if our solid R can be decomposed into smaller solids R1, R2, Rn, which do not overlap significantly, then we have that the volume of the bigger piece is equal to the sum of the volume of the smaller pieces. So let us go forward and look at a concrete example. So here we are looking at a cone. We are looking at a cone with base with radius r and height h. So we may visualize this cone as it is drawn in the figure. So here this is our x-axis, this is our y-axis, this is our origin, and what we are going to do, we are going to draw a line that joins origin to the point h comma r, and this gives us a rectangle that you can see in the picture. And you may also observe that if we rotate this triangle around x-axis, then what you get is a cone. And what is the height of this cone? Well, the height of the cone is exactly the length of the base of this segment, base of this region, which is h, and the radius of the base is going to be equal to r. So now, as we had done previously, we are going to cover our cones with cylinders. We are going to have a network of right circular cylinders which just contain our cone, and also we are going to draw or construct a network of right circular cylinders which is inscribed inside the cone, and our process, our formula, whatever you call, remains the same. So we are going to construct the quantities that we have constructed, un, ln, and we are going to proceed to our business. So let's see what we have done. What we have done in this picture is that I have divided the base of the region, base of this region, into n equal parts, as it is very common in integral calculus. And suppose that here I have picked my kth subinterval and the rectangle around it. So if I rotate this rectangle about the x-axis, you can see that this is going to give me a right circular cylinder. And what is the radius of the base of the cylinder? This is going to be exactly the length of this line, which is perpendicular to x-axis here. And what is going to be the height of the right circular cylinder? It is going to be equal to this part. So length of the partition, so length of the subinterval that we have got from the partition. I'm so sorry about this. So then we know that the height, or which is also the length of the subinterval, is constant because I have divided this base of the region into n equal parts. So this constant is going to be h by n. It will remain constant, and so to compute the radius of the base, we have to now find out the coordinate of this point. So what is the coordinate of this point? We know that this is our kth subinterval, so the x coordinate is going to be equal to kh divided by n. And what is going to be our y coordinate? So we have to put x equal to kh by n in this formula, and we can see that this turns out to be equal to rk by n. So let us now put what we have got, and now we know the formula for the volume of a right circular cylinder. And what is the volume? This is given by pi r square h. So here this acts as our r, this acts as our h. So pi r square h, pi r k divided by n whole square times h by n, which is nothing but pi r square h divided by n cubed times k square. Now we are going to make use of our third axiom, and what we are going to do is that we add up all these quantities. So by this we get k equal to 1 to n, and this quantity pi r square h by n cubed times k square. And this whole thing is independent of k, and this can come out of the summation. So pi r square h by n cubed, and then inside the summation we have k square. And we know how to compute this summation, and this summation is exactly equal to pi r square h divided by n cubed, n times n plus 1 times 2n plus 1 divided by 6. And we have seen before that as n tends to infinity, this goes to this limit, this limit is exactly equal to 1/3. Okay, so not this limit, so when we include this n cubed as well, so this whole limit is equal to 1/3, and what we get as n tends to infinity, this is going to be pi r square h by 3. So even though we have got what we always know that the volume of a cone is given by 1/3 pi r square h, we are not yet there. Instead, what we have done, or what we have proved, is the fact that the volume that we are concerned with is less than or equal to pi r square h by 3. Now we want to also determine what is the quantity ln and the limit. So as we have done before, while computing the areas, we are simply going to determine what is un minus ln. So how do we go about determination of un minus ln? So first we have to construct what is ln. So ln is given by the small rectangles. So if we consider the small rectangles, the network that we get, if we rotate this about x-axis, we are going to get the network of the smaller cylinders, which is just inscribed inside the inside our cone, and the volume of this network is going to give us ln. And so what is un minus ln? You see, un minus ln is a solid which is given by rotating this this regions which I am now shading in white. But this regions, if we only look at xy plane, match exactly very nicely with the region that is given inside the uh, the biggest rectangle. So I don't know, I am running out of symbols, but you can verify that all these things are very nicely fitted into the bigger rectangle, and hence when we rotate the whole network of the smaller rectangles, that is the that comes as this error un minus ln. So you get exactly the volume of the cylinder that is obtained by rotating this whole region, which is the biggest rectangle in the picture. So then what is un minus ln? Un minus ln is nothing but the volume of the right circular cylinder, which is obtained by rotating the biggest rectangle about x-axis. So, and what is that? We know the radius of the base, so r square times h by n, and we always have pi here. We see that pi, r square, h, all these things are constant, and n varies, and the only part that varies with n is the quantity 1 by n, and it is easy to see that this goes to 0 as n tends to infinity. So what have we now got? We have got that our volume is somehow squeezed between un and ln, and we have also seen that un and ln go to the same limit, so v must be exactly equal to the common limit. This is what I have written here. The volume of the cone is given by limit as n tends to infinity un, and we have determined this limit here. This is equal to pi r square h divided by 3.